To understand more about boundary condition, let's discuss two examples related to this topic. Okay, the first example, consider the boundary between medium 1 and medium 2 in the figure below. Medium 1 is air, where epsilon 1 equal to epsilon naught, and medium 2 is a dielectric with epsilon 2 equal to 2 epsilon naught. Assume there is a surface charge density of 0.2 coulomb per meter square at the interface between the two media, and the electric flux density in medium 1 is given by d1 equal to 3x plus 4y plus 3z coulomb per meter square. Determine the electric flux density in medium 2, and then determine angle theta 1 and angle theta 2. That is the questions. And you have to refer to this figure. So from this figure, you can see that there is two regions, and we have a boundary. At the boundary, we have surface charge. And then at region 1, we have epsilon 1. Region 2, we have epsilon 2. And we have the incident field in region 2 and region 1. And at region 1, is given by d1 here. So you have to determine the flux density in medium 2 and determine angle theta 1 and theta 2. That is the questions. So how to find the flux density in medium 2? Of course, we have to relate with the boundary conditions that we discussed earlier. For the solution, the unit vector for the boundary condition is n equal to z. When you observe the surface, so the normal to this surface is z direction. So the unit vector should be z. And the given flux density has the following normal and tangent component. So the normal component should be the z component. So d1 normal equal to 3z. And d1 tangent equal to 3x plus 4y. Due to rho naught equal to 0.2 coulomb per meter square at the interface, the normal component in medium 2 can be obtained with n d1 minus d2 equal to rho s, or d1 normal minus d2 normal equal to rho s. Okay, let's say d2 is given by d2x plus d2y plus d2z in s and y and z direction respectively. So we have to write, okay, the normal component, which is we have to minus the first component with the second component. We know the first component, and then we have to minus with a second component that we rename as this general expressions. So we have z here, and you have to basically dot product with this part d1 minus d2. Of course, when you dot product, the component x and component y will be disappear. So what left is just 3 minus d to z. So we have 3 minus d to z here is equal to 0.2. Therefore, d to z is equal to 2.8, or in the vector form is equal to 2.8 in the direction of z. While the tangent component for d2 is, this is the analysis for tangent component. Hopefully you can recall where E1 tangent is equal to E2 tangent. And E1 tangent is equal to D1 tangent divided by epsilon 1. Because you are given D1. So you have to divide by epsilon 1. So from here, you can find what is the D2 tangents. D2 tangent is equal to epsilon 2 divided by epsilon 1 D1 tangent. Epsilon 2 is equal to 2 epsilon naught. Epsilon 1 is equal to epsilon naught. and d1 tangent is known. So is equal to 6x plus 8y, the solutions. Therefore, the flux density in medium 1 is, we have to combine together, d2 equal to d2 tangent plus d2 normal equal to 6x plus 8y plus 2.8z coulomb per meter squared. So we solve the first questions. Next, we go to the second questions. What is the angle between d1 and the normal line? Since we know what is the d1 tangent and d1 normal, so you can find theta 1 by using this equation, which is theta 1 equal to reverse tangent, the magnitude of d1 tangent divided by d1 normal. This is just by using theorem Pythagoras. So the final answer will be 59 degrees. While the angle between d2 and normal line is theta 2 equal to reverse tangent d2 tangent divided by d2 normals, and the last solution will be 74.36 degree. Alright, we go to the second example related to boundary conditions. Compared to the previous example, this example shows the different coordinate system. Now we have cylinder. The question is, a long cylinder with z-axis as its center has a length of L and side surface of R equal to 3, which separates two homogeneous regions, which region 1 R less than 3, as well as epsilon R1 equal to 2.4 and epsilon R2 equal to 10 respectively. Given E1 equal to 2R plus 5V minus 4Z kilovolt per meter, find A. Electric field intensity E2 and electric flux density D2. B. Polarization vector P1 and P2. C. Bound surface charge density at R equal to 3. And lastly, energy density at all regions. So, we have two dielectric material. One in this region, another one is outside R equal to 3. And then you are given E1. From this question, you can see that you have to find out what is a E2, D2, and polarization vector at both regions, because both regions are dielectric. So polarization vector exists inside dielectric. And then bound charge density at the surface and energy. Alright, let's see how to solve this. So we can see here that the region is divided into two regions at R equal to 3. So we have the region where R less than 3, and then we have another region when R greater than 3. It has the different material properties. Here you are given epsilon R1, which is relative permittivity. So make sure you can differentiate between permittivity and relative permittivity. Well, this is the figure. So you have to analyze this figure and you have to know which one will be the normal component and which one will be the tangential components. Refer to this figure, you can see that the normal component to the surface is always going in R directions, it's going out. So you are given the E1 equal to 2R plus 5 phi minus 4z kilovolt per meter. So E1 tangent should be 5 phi minus 4z and E1 normal is 2r. D1 tangent is equal to epsilon 1 E1 tangent equal to 2.5 epsilon naught. So you have to add epsilon naught because you are given epsilon r. So here you have 2.5 epsilon naught E1 tangent and equal to 12.5 epsilon naught phi minus 10 epsilon naught z. Electric field intensity E2 and electric flux density D2. We know from the boundary condition E2 tangent is equal to E1 tangent equal to 5 phi minus 4z. And the E2 tangent is equal to D2 tangent divided by epsilon 2 equal to E1 tangent. Therefore, D2 tangent is equal to epsilon 2 E1 tangent equal to 10 epsilon naught 5 phi minus 4z. And you get here 50 epsilon naught phi minus 40 epsilon naught z. For D2 normal equal to D1 normal, where D1 normal equal to epsilon 1 E1 normal. The E1 normal is 2R, epsilon 1 equal to 2.5 epsilon naught. So we have 2.5 epsilon naught 2R. So we got here 5 epsilon naught R. So we can find the E2 normal by dividing D2 normal with epsilon 2 equal to 5 epsilon naught R divided by 10 epsilon naught is equal to 0.5 R. Therefore, E2 is equal to 0.5 R plus 5 phi minus 4z kilovolt per meter, and D2 equal to 5 epsilon naught R plus 50 epsilon naught phi minus 40 epsilon naught z kilocoulomb per meter square. So we solved the first question. We go to the second question, which is about polarization vector P1 and P2. From previous analysis, D1 equal to 5 epsilon naught R plus 12.5 epsilon naught phi minus 10 epsilon naught z coulomb per meter square. Hence, the P1 equal to D1 minus epsilon naught E1. So, substitute everything that we know. So, the P1 is equal to 3 epsilon naught R plus 7.5 epsilon naught phi minus 6 epsilon naught z kilocoulomb per meter square. So, P and D will have the same unit. Similarly, for P2, polarization vector in medium 2 is equal to D2 minus epsilon naught E2. And then you have to change D2 and E2 that you find before. So, your final answer will be 4.5 epsilon naught R plus 45 epsilon naught phi minus 36 epsilon naught z kilocoulomb per meter square. So, we solve the second questions. For the next questions, bound surface charge density at R equal to 3 meter. When R equal to 3 meter, we should take both region for analysis. Okay. So we have in region 1 we have P1, and this is the unit vector R. And then we have P2 in region 2, and this is a vector unit actually normal to the surface, right? P2 the normal is going inside, so negative R direction. So for P1 is going out, positive R directions. So to determine the OSB at R equal to 3 is basically equal to P1 minus P2 dot product with the normal vector, where N is a unit vector normal to the surface of region 1 at R equal to 3. So in this case we take N equal to R. Therefore OSB equal to, you put everything, you know P1 is what, P2 is, as you determined before. So your final answer will be minus 1.5 epsilon naught kilo coulomb per meter square, because your unit vector is R, therefore only component R will exist to determine the OSB. For the last question, we will determine the energy density at all regions. So the total energy density is equal to energy density in region 1 plus energy density in region 2. This is our structures. Let's say in region 1 we have E1 and epsilon 1. In region 2 we have E2 and epsilon 2. So we will use this formula to determine the energy, which is Wn equal to 1 over 2 epsilon n En square. In region 1 we have W1 equal to 1 over 2 epsilon 1 E1 square is equal to 1 over 2, 2.5 epsilon naught, and then the E1 here, it will be magnitude. So we have to square root the magnitude of E1. We have 2 square plus 5 square plus 4 square. And your final answer will be 56.25 epsilon naught millijoule per meter cube, because this is energy density, which is per volume. Or when I just put the epsilon naught, so the answer will be 4.98 multiplied by 10 power of minus 7 joule per meter cube. With the similar arguments, W2 equal to 1 over 2 epsilon 2 E2 square. Just put everything that you know. So your final answer will be 206.25 epsilon naught millijoule per meter cube, or 1.826 multiplied by 10 power of minus 6 joule per meter cube. So you have to add these two energy together, which is W1 plus W2, to find the total energy density. That's all.